Griffiths E&M Example 2.9, which is in section 2.4.3. We have a couple different ways that we can calculate the energy of a charge distribution. So we're going to go ahead and compare two of those methods. Okay, so the goal here is to use two methods to calculate the energy of a uniformly charged spherical shell. So radius r, spherical shell, so surface charge density sigma. It has a total charge q and a radius r. Okay, so let's do this. Let's do the first way using the adapted version of equation 2.43. 2.43 tells us that the energy of a charge distribution is 1/2 the volume charge density, the potential at points in space, integrated over all space. We're dealing with something that's in 2 dimensions that has a surface charge density, so this is 1/2 sigma v dA. Okay, in previous examples, you have already found what the potential of this sphere is, and specifically we want the potential at the surface. Okay, that is, just write down the expression here, sigma 1/4πε0 q over r, integrate over dA. That's a nice integral to do because everything seems like it's a constant here. So that's a 1/8πε0 sigma. Oh, that one's still the integral. Q over capital R sigma dA. Or just the integral of all of the charges over all the surface is Q. So I'm left with 1/8πε0 Q squared over R. Right, so I evaluated the potential at every point along my surface to that integral and got some value. Okay. So we can do this another way. All right, let's see, borrow this expression from example 2.7. All right, and then instead of integrating over the charge density times the potential, we can go ahead and figure out what the electric field is, and then we can go ahead and integrate over all space, the square of that. Okay, so all space, our bounds are picked for us. So we need to figure out what the electric field is throughout all of space so we can integrate appropriately. All right, inside of our charged shell, the electric field is 0. All right, Gauss's law gives us 0. Outside, we've done this a couple of times probably. This is 1/4πε0 q over r squared in the r hat direction. All right, and then I go ahead and square E out. That is q squared 4πε0 squared times r to the 4th. Right, the squaring was a dot product really, so the magnitude is this. So I can calculate the energy of this distribution by saying, all right, let's go ahead and take the integral over all space inside my sphere plus outside of my sphere I included this, but we know it's 0 because E inside is 0. Okay, now we're left with calculating this integral over the outside, and the outside bounds are going to be some capital R to infinity with some solid angles of q squared over 4 pi epsilon naught squared r to the fourth times d tau. Okay, d tau is r squared sine theta d phi dr. Great. I don't have any angular dependence, so my integral of all of my thetas and phis gives me 4 pi epsilon naught over 2, 4 pi q squared, 4 pi epsilon naught squared. Oh, can't pull that out. Capital R to infinity. R squared over r to the fourth, that's 1 over r squared dr. That can be evaluated, and we get 1 over 8 pi epsilon naught q squared over r. All right, those are exactly the same as they should be. So there are multiple different ways that you can calculate the energy of a configuration. You can either integrate the electric field squared over all of the space. You can do this integral of the charge distribution times the potential over all space. There's even the intermediate version where you integrate over the electric field squared and some version of the potential over a surface. And you should always get the same answer. So it's kind of nice to have the opportunity to check your work instead of just having to believe that this is correct.